Hi, let's try to solve the following second order non-homogeneous differential equation. And the question like specifies to say we need to use the method of variation of parameters. So the general solution that you're going to get for this differential equation that you have right here by using the method of variation of parameters, how you're going to go about is that the general solution that I indicate using y will be equals to my complementary function, okay, plus my particular solution. So the big deal is about how do you get your complementary function and how do you get your particular solution. So let me first of all highlight all the things that you need to do for you to get your complementary function as well as to get the particular solution, because questions will not always appear the same. Like they are not always going to be the same. So let me just give you an outline of how you can solve any question when it comes to you using method of variation of parameters. So um, for the complementary function, it all depends on the roots that you have. So what I mean by the roots is when you look at this non-homogeneous differential equation that you have, what you first of all need to do is to solve the homogeneous part of this. What I mean is for me to take this as homogeneous, meaning this is supposed to be d2y dx2 plus y is equals to 0, instead of me having uh, this than x here. So I'm going to equate this to 0 so that it becomes a second order homogeneous differential equation. Then solve the auxiliary equation for that one there. Okay, so solving the auxiliary equation, I believe, is very simple. We just let this be equals to m squared plus 1 be equals to 0. Okay, so meaning your m is going to be equals to positive or negative I. The question is, how have I come up with that? Is because I have like my m squared being equals to negative 1, meaning my m will be equals to positive or negative the square root of negative 1. We know what negative 1 is. It's simply I. So what it is here is that you observe that I've gotten complex roots. So you don't always get complex roots. It might be real distinct roots, it might be real equal roots, or it might be complex roots. So if you get complex roots as we have, your complementary function, so let me just say for complex roots, you're going to say your complementary function, which I'll just indicate as, in fact, let me just indicate as complementary function in this case. This is just for this case, but for other cases you can indicate it just as y. So you can say our complementary function is just going to be equals to, for complex roots, it will be equals to e px, e to the px, then open bracket a cos qx plus b sine qx there, like that. So now, where does the p come from? Where does the q come from? When it comes to complex roots, you're going to get them in the form p plus or minus um, qi. Okay, there will be, to the answer that you're going to get, there will be a real part, a p, and there's a coefficient of the imaginary part, which is q. So this is what you're going to substitute here. So if you observe here, okay, if you observe here, we just got positive or negative I, meaning the coefficient of I is a 1, and you don't have a p. So here for the p is going to be what? It's going to be a 0. So now let's look at a situation where if we had, let's say, real equal roots or real identical roots. Let me just say real equal roots here. If you had real equal roots, your complementary function could have been written as uh, complementary function being equals to you say a plus bx here, then here you're going to have e to the mx. The reason why I'm saying m here is simply because when you get identical roots, meaning your m1 is equals to your m2, hence you can just indicate this as what? As m. Okay, so now let's look at the third part, which is the real distinct roots. Okay, real, let me say different roots or distinct roots, whichever, it's the same. So for real distinct roots, you can say your complementary function will be equals to a e to the m1x plus be to the m2x. And this is a situation whereby, let's say for example, I said your m1 was equals to 1, then maybe your m2 was equals to a 5. This is what you use, this is what we mean when you have real distinct roots. So by the way, if you know everything that I'm talking, if you already know what I'm talking about here, like how to identify everything, you can skip the video to the part where I'm finding the solution. Okay, so now we have known how to come up with the complementary function. How do we then come up with a particular solution? Because we'll add the complementary function plus the particular solution to get our general solution. So your particular solution is just going to be equals to u1 by y1. Okay, u1 by y1 plus u2 by y2. So the method that I'm using here is a method of variation of parameters, and I'm going to use Wronskians to find my particular solution. So the question is, what is my y1 and what is my y2? That's the simplest thing that you can get on this part. So your y1 and your y2, for example, if um, if let's say for example we had real distinct roots, this here could have been your y1, this here could have been your y2. Okay, and when you expand this one here, because when you expand this one, this just will be equals to be something like a e to the mx plus bx e to the mx there. So this right here could have been our what, our y2, this could have been our y1, like that. Okay, so when you get your y1 and y2 from the complementary function, so it's important that you get the correct complementary function. So where then now do we find our u1 and our u2? So here we are going to use Wronskians. So for Wronskians, you're going to say w representing Wronskians will be equals to our y1, then here you're going to say y prime of 1, then here you're going to have your y2, then y prime of 2, like that. Okay, then you also have to find your w1, which will be indicated as you're going to have your 0 here, then g of x. I'll explain where you get the g of x. Then this side you're going to have your your y2, then y prime of 2, your y prime of 2 there. Then your w1 will be equal, sorry, your w2 rather will be equals to this is going to be equals to your y1, then what sorry, that would be y prime of 1 there, y prime of 1, then you have your 0, then your g of x. So where you get your g of x, which is this one here and that one there, is just simply what you have here after the equal sign of the non-homogeneous, of the second order non-homogeneous differential equation. So how do we then take advantage of what we have here to get our u1 and our u2? So our u1 will be equals to the integral of w1 divided by w here dx, then our u2 will be equals to our integral of w2 divided by w, then dx, like that. So everything that I've shown you here is all you need. Okay, this is all you need to solve any differential equation by method of variation of parameters. There might be other methods other than Wronskians, but I feel Wronskians is much straightforward compared to maybe other methods or of solving the, like finding the particular solution. Because if I get this one, I get my complementary function, I just add them together, then I have my my general solution. So now Let's now use everything that we have understood at this stage to come up with our solution. Okay, so actually you can even try to pause the video, try to work it out on your own from what we're just from explaining, then compare the answers at the end to see if we're going to get the same thing. Okay, so now let's first of all find the complementary function. Of course, you have to solve the auxiliary equation here. So this will be m squared plus 1 will be equals to 0. So you remember we said our m was equals to positive or negative I, meaning we are dealing with complex roots. So meaning our complementary function will be equals to e to the p. What is our p? It's 0x. Then you have your a cos qx. What's our q? Our q is 1, so we just say x here, plus our b sine qx. Our q is 1, so you just say x there, like that. So this portion here gives us a 0 because any number raised to the power 0 is going to be a 1. So our complementary function is just going to be equals to a cos x plus b sine x, and there we have it. It was as simple as that. Okay, so we have our complementary function. Let's now look for the particular solution. So remember we said our particular solution is just equals to u1 by y1 plus u2 by y2. Let's determine what our u1 is. Remember, for us to do that we have to find what the value of Wronskians is, or the expression. So this is equals to, we said our y1 is going to be this part here. Okay, so let me even indicate to say this is our y1, this is our y2. I don't mean y1 being a cos x, it's just cos x, which is the coefficient of this constant here. Coefficient, let me say this one is the coefficient of this one. Okay, or you can say this one is the coefficient of that one. Anyway, you understand what I mean. Yeah, so this part here is our y1 and this part is our y2. So our y1 we say is cos x, we say it's a cos x here. Then our y prime of 1 is minus sine x. That is when you differentiate cos x. Then our y2 is sine x, our y prime of 2 is cos x. Okay, so just find the determinant for that part. So if you multiply the major diagonal, you're going to get cos squared x. Okay, then the minor diagonal is supposed to be minus, open bracket, minus sine squared x. So observe that minus times minus gives us positive, so cos squared x plus sine squared of x just gives us a 1. We know this from trig identities, so we have gotten to say our value of Wronskians is just equals to 1. So let's get our w1. w1 is just equals to, we said we put 0 here, then here put g of x, which is our tan x. Then y prime, our y2 is sine x. Then y prime of 2 is cos x. Okay, so finding the gradient of that one, we just find out that it's minus tan x sine x there, like that. So our w1 is equals to minus tan x sine x. Let's look for our w2, which will be equals to our y1, which is cos x, then y prime of 1, which is minus sine x, then our put 0 here, then our g of x is tan x. Our minor diagonal gives us 0, major diagonal gives us cos x multiplied by tan x. What's tan x? Tan x is the same as sine x divided by cos x. So that cancels and that cancels. So try your level best to simplify what you have as much as you can. So this is just sine x, like that. So now let's go ahead and find our u1 and our u2. Okay, so our u1 will be equals to the integral of w1 which is minus, so I'll put the minus here, tan x sine x there dx. Okay, I'm supposed to say divide by w which is a 1, but I don't need to put it anyway. So if you integrate this one, you can check it out from the table of integrals. Your u1 is just going to be equals to this will be equals to sine x minus natural log of tan x plus sec x. Okay, that's what we have. So now let's look for our u2. u2 is going to be equals to the integral of w2 which is sine x divided by w which is 1, integrate with respect to x. So our u2 will be equals to nothing but minus cos x. Just a reminder once again, how you get these derivatives and integrals for cos and sine is very simple and fun. Okay, so here you have cos x, is it cos x? It's actually sine x here. Then you're going to have cos x there. Then here we have minus sine x. Then here you have minus cos x. So when I'm going like this, I'm differentiating. When I'm going like this, I'm integrating. So if you say integral of cos, you just come once like that, that's minus cos. So that's how I get that one. Okay, so there we have our u2 and our u1. So we can go ahead and compute our particular solution. So particular solution is just going to be equals to, what's our u2? Let me just try to move it here. Our u2, sorry, our u1, we have found this here. Okay, so to save time, let me just try to copy this. Okay, I can place it right there, then multiply by y1 which is cos x plus, okay, our u2 is minus cos x multiplied by y2 which is sine x. Expanding this, you get that your particular solution will be equals to this one multiplied by this one is going to be sine x cos x minus natural log of 1 natural log of tan x plus sec x there like that. Then that will be by cos x, because when you multiply this one and that one, that's what you get there. Then that one there is just going to be minus sine x cos x. So this is beautiful because this goes and that goes like that. So we have something that is simplified. So I can cancel that one and this part. So this is what we have as our particular solution. Then we just have to add this to the what, to the complementary function for us to get our general solution. So this now ends up to be to say your y representing the general solution is just going to be equals to your complementary function, which is a cos x plus b sine x minus your particular solution, which is supposed to be plus because it's minus here. I just say minus natural log of tan x plus sec x, and this right here is your what, is your general solution. So this is how we apply method of variation of parameters, by taking into consideration how you go about using using Wronskians. And it's very important that you know how you come up with your complementary function, and we get those by using a trial solution, which is y is equals to a e to the mx, and you try to determine, do you have real identical roots? So do you have real distinct roots, or do you have complex roots? And that's going to guide you in terms of like the how the expression of your complementary function is going to be. So it's, remember, it's key that you find the correct complementary function, because it's going to guide what you're going to get as your particular solution. Because from the particular, I mean, from the complementary function, you get your y1 and your y2. That is what helps you to come up with your particular solution. So that's all in this video. Thank you very much for watching, and we'll see you in the next one.